For more than 2 centuries, we've known that there is a much higher proportion of dolomite in the ancient than we can scale into the ancient looking at the distribution of modern or Holocene and Quaternary dolomite occurrences. And this is called the dolomite problem. The drivers for this are not well understood, but most would agree it's some sort of combination of changes in longer-term climate and also changes in the chemistry of the world's oceans associated with regions of dolomite formation. So, to state the dolomite problem, we know that dolomite is rare in Holocene sediments, and we'll look at the examples of this in subsequent modules. We know that reaction rates that precipitate dolomite from a solution are very low at room temperature. We've failed to make non-biogenically facilitated dolomite in the lab at conditions relevant to Earth's surface temperatures and pressures. We know that modern oceanic chemistry is supersaturated with respect to dolomite, and yet dolomite is a very rare primary precipitate on the seafloor, and many have argued that this is related to kinetics. There's not sufficient time to form large volumes of dolomite, and those volumes of dolomite that do form tend to be metastable. They tend to be non-stoichiometric. There's not a one-to-one distribution between calcium and magnesium. And in the last 3 decades, we've found that dolomite evolves through time in the subsurface, in the eogenetic and the mesogenetic realm, toward a more stoichiometric association. And we also know that this process is a combination of dissolution and precipitation throughout the time that dolomite spends in the subsurface in zones that are sufficiently permeable to allow the crossflow of dolomitizing solutions. At the longer term scale, people have argued that changes in the levels of magnesium in the world's oceans have changed, driven over the scale of tens of million years by changes in the rates of seafloor spreading, and that this changes relative levels of calcium to magnesium in the ocean, and hence will affect the oceanic chemistries suitable for dolomite precipitation or dolomite replacement. We also know that due to changes in the levels of magnesium and sulfate in the ocean, at times when we are precipitating large volumes of magnesium sulfate depleted evaporites, as we did in the Cretaceous, we may also drive an oceanic chemistry that's more suitable for dolomitization in the world's carbonate platforms. We also know that there are long-term fluctuations not just in the magnesium to calcium ratios, but also in the partial pressure of carbon dioxide. And so this too will affect the suitability of widespread dolomite precipitating fluids in the world's oceans and in the near surface. And we also know that levels of oceanic oxygen have changed from the Proterozoic into the present day, and that this may in turn relate to changing levels of anaerobic bacterial metabolisms, which facilitate the precipitation of early or penny-contemporaneous dolomite. And we'll address each of these factors in the subsequent module dealing with the chemistry of dolomite precipitation and replacement. So if we consider the long-term fluctuations, we know that the world's climate has oscillated a number of times between greenhouse and icehouse climate. In icehouse times, we have significant volumes of ice at one or both poles, while in greenhouse times, there is little or no polar ice. There may be continental glaciers, but we don't have large permanent sheets of ice located above the north and the south poles. So this fluctuating or oscillating temperature changes related to greenhouse and icehouse climate may affect the levels of dolomite precipitation as we change the world's latitudinal temperature profiles across the carbonate platforms and the extent of the carbonate platforms of the world. And of course, this is also related to the fact that we may be putting water back into the oceans when we melt the ice sheet, so this will change the levels of epiric seaways. And there are also significant differences between greenhouse and icehouse climate that relate to the nature of the eustatic curves at the higher order levels between greenhouse and icehouse climate modes. So in icehouse climate mode, fourth order sea level oscillations tend to fluctuate on the scale of 100,000 years with amplitudes of the order of 100 meters. Whereas in greenhouse times, when there are no polar ice sheets, we don't have the expansion and the contraction of the world's ice sheets controlling the nature of the eustatic curve. And so in greenhouse times, we see fluctuations at the 100,000 year or fourth order scale of quite low amplitude, less than 10 meters. And also because in greenhouse times we have melted the polar ice caps, we see much higher levels of absolute sea level, and so a much greater proportion of the world's cratonic areas are covered by the sea, which facilitates the formation of epirich, pericontinental and epicontinental seaways. So relating this back to dolomite precipitation, it leads to the notion that with widespread shallow seaways across the world's cratons and along much more extensive continental margins, we may see a propensity for dolomitization at times when we have elevated magnesium to calcium ratios and perhaps higher salinities related to warmer climates and higher rates of seafloor spreading. And this has led many to argue that dolomitization is favoured by greenhouse climate and greenhouse eustatic styles. So during greenhouse times, when the world's sea level is higher than it is today in our current icehouse mode, we have much greater extents of marginal seaways, epirich seaways, epicontinental basins, and also much more extensive carbonate platforms, both within the tropical and the subtropical belt, but also much more extensive tropical and subtropical belts with chemistry suitable for dolomitization because we have a much warmer latitudinal profile in the world's climate. But we all know that correlation is not necessarily causation. We do know that changes in the rate of seafloor spreading will alter the composition of both the atmosphere and seawater, and this in turn will drive climatic fluctuations. And so in greenhouse times, we'll see increased CO2 levels. In greenhouse times, we'll see elevated eustatic levels, and also we will see much lower amplitude, fourth and fifth order cyclicity in the world's eustatic curves. We will see lowered saturation states in seawater with respect to calcite. We will see times when the magnesium to calcium ratio is much higher and hence more suitable for the formation of dolomite. And we may have times when we have lowered atmospheric oxygen levels related to increased levels and rates of bacterial sulfate reduction, also creating the propensity for dolomitization. So let's have a look at some of these correlations, which may or may not be causative. So this is a plot of carbon dioxide levels across the Phanerozoic, and it's also related to the icehouse versus greenhouse climate modes. And very clearly it shows a correlation between elevated CO2 levels and icehouse versus greenhouse effects, with the greenhouse times having much higher levels of CO2 in the world's atmosphere compared to icehouse mode climate. And we can also see how in greenhouse times we have much more elevated average world temperatures, up around 22.5 degrees centigrade versus around 12 degrees during icehouse mode climate. If we now put the proportion of dolomite from a curve by Given and Wilkinson back in 1987 and relate it to that icehouse greenhouse mode climate, and in this case the lower diagram is showing you icehouse versus greenhouse times, and it's also showing you levels of glaciation. And notice that with the exception of the Neogene, we did not have bipolar glaciation. In previous icehouse mode times, we only had an ice sheet at one, not both, of the world's poles. You can also see in this curve that most of the world's Phanerozoic history is characterized by greenhouse mode climate, not icehouse mode climate. So we live in unusual times. Looking at the dolomite curve, we can see that across the Phanerozoic, there are times when dolomite was more common. This is especially obvious in the Ordovician to the Middle Silurian and in the early Cretaceous. And this shows a very broad correlation to levels of epirich seaways and greenhouse eustacy. So perhaps, if correlation was causation, we could argue that elevated CO2 encourages dolomitization. Let's put the eustatic curves and a number of different calculations on that curve of dolomitization, and you can see that there is an approximate correlation between this curve by Given and Wilkinson between dolomitization and relatively elevated sea levels. Here's the CO2 curve to remind us icehouse versus greenhouse. So at first order, given this Given and Wilkinson curve, many have argued that it is the CO2 levels in association with eustacy that gives us a causative correlation between dolomitization and world climate and world atmospheric chemistry. But as we said, correlation is not causation. Let's have a look at another couple of tentative correlations with world scale processes. This Next slide comes from a curve by Lee et al., published in 2021, where they plotted dolomite abundance in purple, and in the lower curve, they're showing us the extent of carbonate shells across the Phanerozoic. With this more recent data set of dolomite occurrence, we can see that the curve is a little different to the curve published by Given and Wilkinson back in 1987. And what Lee et al. Argued was that if we look at the peaks in the dolomitization curve and we relate it to the biodiversity in the lower curve, which is plotting genera through time, you can see many of the dolomite peaks correspond with significant extinction events. This is the Big Five major world-scale extinction events that correlate with peaks in the dolomitization curve, with the exception of the Triassic-Jurassic. Let's have a look at another correlation. And in this case, we're plotting major evaporite events, shown in red, versus the dolomitization curve. And this first curve in the evaporites gives you the timing. If we remove that to make it a little clearer, you can see that many of the peaks in the dolomitization curve, with the exception of the Cretaceous, the broad general highs correspond to levels of world-scale, basin-wide evaporite times. And some have used this to come up with the notion that dolomite is more related to being in association with hypersaline conditions, and it is an evaporite mineral, as Jerry Friedman argued back in the 1960s. But none of these correlations are perfect, and none of them are single drivers, and it's much more likely that we're seeing a combination of factors with varying intensities of those factors over time that at the broad scale, the broad time scale of the Phanerozoic, are driving broad scale changes in the intensity of dolomitization. So what don't we know in terms of the dolomitization problem? We still have no idea why there's so much ancient dolomite and so little modern dolomite in terms of a quantified hypothesis. We really don't know how the chemistry of ancient dolomite forming settings changed across the Phanerozoic and what factors were important in controlling proportions of dolomites in the world's carbonates across geological time. We don't know how the volume of dolomite precipitation has changed in a fully quantified fashion. There are conflicting curves. We don't know the importance of kinetics versus parity in dolomitization. We don't know if dolomite formation is controlling ocean chemistry or if ocean chemistry is controlling dolomite formation. And we don't know what are the effects of bacterial mediation on dolomitization or dolomite precipitation versus other mechanisms. And we'll discuss each of these in detail in the following modules and chapters.